Welcome to combining the localized electron and molecular orbital models. So the localized electron bonding model works quite well for molecules that don't exhibit resonance and don't have odd numbers of electrons. So for molecules that do exhibit resonance, we have to use the molecular orbital model. But the molecular orbital model is significantly more complicated. It's significantly harder to use, which means that if we can somehow combine the localized electron bonding model and the molecular orbital model, maybe we can get a model that accurately predicts molecular orbital or molecular bonding, but is simpler than the molecular orbital model. One that works in most cases, but is a lot easier to use than MO. So let's examine the resonance in ozone, O3. So the localized electron model successfully predicts the sigma bond behavior. So one sigma bond exists between each of the outer oxygen atoms here and the central oxygen atom. So that is, the electrons in a sigma bond are localized. They're localized between those two nuclei. But the localized electron model fails to adequately predict or to accurately predict the sharing of the sigma bond among the two outer oxygen atoms. So amongst these two oxygen atoms, it can't predict that resonance, that sharing of the electrons. So that means that electrons in a sigma bond are delocalized electrons, but the electrons in a sigma bond are localized electrons. So we can then combine the localized electron and molecular orbital models such that the sigma bonds are accurately predicted by the localized electron model. So electrons are localized in the space between the two atoms, between the two nuclei. And the pi bonds are predicted by the molecular orbital model. So electrons are delocalized over all the atoms available for pi bonding. And if a molecule doesn't exhibit resonance and doesn't have an odd number of electrons, then the localized electron model is sufficient to describe its bonding. So if we don't have any resonance, we don't have a radical, we don't have any odd numbers of electrons, then the localized electron model is good enough to describe its bonding, to describe its shape and things like that. If we do have resonance, if we do have an odd number of electrons, then we have to turn to molecular orbital model, at least for the pi bonds. So now let's look at a very important molecule for organic chemistry, which is benzene. So C6H6, it looks something like this. We see resonance in the ring, right? We've got carbon atoms at the center of these, at the vertices here. So we have 6 carbon atoms there, 6 carbon atoms, 6 hydrogen atoms around. And you note that we can switch these, we can move each of these double bonds clockwise or counterclockwise by 1 and end up with this structure. We can continue doing that. But what actually ends up happening is that each carbon atom is sp2 hybridized. Each carbon atom has then one unhybridized p orbital. Furthermore, because of the orientation of all of the carbon atoms, each of those unhybridized p orbitals are all perpendicular to the ring, which means they're all parallel to each other. And we now have on top and below the ring, we have 2 concentric circles. They're not concentric circles. We have 2 circles that match the circumference of this ring. One sort of donut shape above the nuclei and one donut shape below the nuclei. And that's where all of those pi bonds are. So there are 3 bonds, but delocalized amongst all 6 of those, all 6 of these carbon atoms. And so this sort of structure is what we call aromatic. When we get a ring structure like that that has these alternating double and single bonds, we call that an aromatic structure. It's a very important sort of structure in organic chemistry. So that was combining the localized and molecular orbital